सर केवल ये स्टॉक स्ट्रीमिंग ಮಾಡ್ದೆ ठीक है सर सर ये लिंक ଯଦି ଆପଣ ମୋତେ ପଠେଇଦେବେ ମୁଁ ଟିକେ ଚେକ୍ କରିବି ଆପଣଙ୍କର
ये जोड़े सार में दिले यूट्यूब
यूट्यूब लिंक शेयर କରିଦେବି ମୋ ନମ୍ବରଟା ଆପଣଙ୍କ
ମୁଁ ପଠେଇବି କେମିତି
ମୁଁ ହ୍ୱାଟ୍ସଆପ୍ ପଠେଇଦେବି
ମୁଁ ପୁରା ଆଉ ଗୋଟେ ଷ୍ଟୁଡେଣ୍ଟକୁ ପଠେଇ ଦେଇଛି ତ ଆପଣ ହ୍ୱାଟ୍ସଆପ୍ଟା ମୋତେ ନାହିଁ
ଠିକ୍ ଅଛି ନମ୍ବରଟା 965 708 जी सर ठीक है चेक करते
ଆପଣ ଅଡ଼ିଓଟା ଟିକେ ଅନ୍ କରିଦେବେ ମୁଁ କରୁଛି ଷ୍ଟପ୍ଟା ହେଉଛି ଆଜ୍ଞା ଷ୍ଟପ୍ ହେଉଛି ଷ୍ଟପ୍
अपन जब
ଏଇଠି ଷ୍ଟପ୍
ठीक है
चेक करिए लैपटॉप में आसुच ठीक है थैंक यू Okay. Good morning, everyone. Thank you. So yesterday we looked into a session that we were applying thermodynamics principles, law of conservation of energy principle to combustion system, and we tried to estimate what is the energy content of a fuel, what kind of temperatures will you get when you burn that fuel, right? With an appropriate amount of oxidizer, if you supply it along with the ignition energy, then what will be the approximate theoretical value of the temperatures, flame temperatures that you will experience. Okay, so what are those temperatures for? Anyone remembers? Adiabatic flame temperatures, and we derived an expression for constant pressure systems, and we saw that those are constant pressure, constant enthalpy processes. All right. So today what we are going to do is, now that we have understood how we can calculate energy content, what could be the flame temperatures that are important to us, the next part is how fast a reaction happens. Right? Yesterday in the afternoon session, Professor Sunil Kumar's session, we were doing some FDS simulations. So one of those parameters, if you remember, was some heat release rate per unit area. Right? So what is that heat release rate? How do you get that? So that is basically happening because of how fast your reactions happen. So in that, to understand that, we have combustion kinetics to help us out, right? So yesterday we looked at this flame propagation, correct? And how fast this flame is propagating is something that we are interested in. Right. So to determine how fast a combustion process happens and how it affects the flame propagation rate, other phenomena like flashback and blow up, which are important for you to have stable combustion, and as well as to calculate these heat release rates, you need to understand combustion kinetics. Okay. So now if you look at, if I freeze this flame front at a particular location, and if I zoom in, what is this basically representing is, this is your flame front, okay, your reaction zone, that is taking place, exothermic reaction zone. On the downstream side, you have your burnt mixture, so these are all burnt products, and on the upstream side, you have unburnt fuel air mixture. Correct. So, and progressively, the flame front is trying to consume the fresh air mixture, fresh fuel air mixture, and it is progressing ahead. All right. So now, if so, I ran a simple 1D flame simulation, and if I plot the various properties, what we'll see here is, so you can see on the x-axis you have distance, right? So this is 0 to 5 centimeters. So there's a 5 centimeter that I have taken, a domain that I have taken, and I've simulated this flame front. So what you see is on the left hand side, y-axis, these are mole fractions. On the right hand side, these are the temperature. Okay. So this red line is basically representing the temperature as you go from the upstream side to the downstream side. So initially you have what do you say? You have 300 Kelvin, which is your ambient temperature, and you see suddenly the temperature has risen up to around 2200 Kelvin, right? So 2200 Kelvin is what we got yesterday, right? For methane air mixture, adiabatic flame temperatures were of that order. So you see that the temperature is rising sharply. And also, if you look at the mole fractions of species compositions, for example, methane is this green line, and oxygen is this dashed line, short dashed line. You see that they're constant till a certain time, and after that suddenly drops. Right? That means they are basically getting consumed in this narrow region, and as they are getting consumed, the products of combustion that are CO2 and H2O are basically rising up. Correct. So now to want to appreciate this, you look at the thickness, the size of this domain, right? So it is very, very narrow. So you have a 5 centimeter domain, and within that also this are basically taking place as if it's instantaneously happening. Now, if you zoom it in, so these are basically zoomed in views of that. So now what we have done is I have zoomed into that plane region, and you can see that this is the temperature profile. So you can see a much more generous gradient. So you can look at the temperature rising, and this temperature rising is happening within. So this is around, let's say, 2.05 centimeter, and now it has almost reached around 2000 Kelvin by 2.15 centimeter, right? So that is roughly around 1 mm. Okay, so the all the temperature rise is happening within 1 millimeter space. Okay, so you can see how thin these flame fronts are. And similarly, you can see all these reactions, the consumptions are also happening within that same length. Correct? Now these are, so on the right hand side, so what I have done is along with the species concentration profiles, I have plotted a heat release rate profile. So this red solid line is basically representing the heat release rate that is happening. Okay, so heat release rate will happen because of what? Heat release will happen because of exothermic reactions, right? Overall, exothermic, endothermic, both type of reactions are there, but the net effect is the exothermic reaction. Because of that, you have the heat release happening. So if the heat release is happening in this domain, everyone said it is almost zero. So what that means is all your combustion reactions are happening within this narrow zone of 0.5 mm. Okay, so that means even if you have, like, you look at this large space, and if you further zoom in, you will get that all your reactions that are happening within this 0.5 mm of space within a conversion front. Okay. Now, in order to estimate this, so this is one of the values that you probably need during your FDS simulations, right? And to calculate this, right, in order to calculate the heat release rate, you need to understand how fast these reactions are going on and how it depends on the fuel composition. So if you look at this generic species conservation and energy conservation equations, so you will see that you have, like, for species conservation equations, you have this term that is basically showing the rate of change of mass of a particular species per unit volume, right? So, and on the energy equation, energy conservation equation term, you again have a source term, which is basically representing the rate of enthalpy increase that is associated with a particular species. So the summation of all those things will basically give you the heat release because of the chemical kinetics. So what we want to understand is, in order to solve these conservation equations, we need to understand how fast a particular fuel, oxidizer, or any species is getting consumed or produced. Right? Yes. A is a basically a species. So if you remember yesterday, so if you have uh, a generic reaction, right? C plus D. So you want to see how fast this species is going. So A basically represents one species. So similarly, we will have B, C, D, whatever the number of species, right? Okay. So now let's look at this. So yesterday we looked at a generic, your stoichiometric methane air combustion reaction, right? So this is one way how you can determine, like, represent this methane oxidation or methane combustion reaction. Okay, so in case one, your fuel has to interact with oxygen molecules so that it gets converted to CO2, carbon dioxide, and water vapor. Correct. So this is one way to represent. The other way to represent is going through this a series of reactions, right? So if I ask you, in reality, in practical situations, what happens? Does your methane directly react with oxygen, or does it go through this series of steps? Series of steps. Why do you think so? Why is this not happening? Why is there not a direct conversion of methane by oxygen to CO2? Okay, so they both have molecular reactions. Right, but what is the problem of this? CH4 is a stable structure. Oxygen is also a stable structure. But when once you start, so if you look at here also CH4 is a stable structure, right? But then when you supply that initial energy to the oxygen, yes. Okay, okay. So, all right. So when we are looking at these reactions that are taking place, we have to kind of look at the probability of this reaction happening versus the other reaction happening, right? So, for example, if you want to look at the left hand side reaction, okay, so if I draw a CH4, so this is a CH4 molecule, right? And then you have, so these two molecules have to interact with each other, okay? Now, from this to go to directly CO2, you basically have to break all these bonds simultaneously, okay? And then this goes and attaches to form CO2. Okay, so the bond between these guys have to break, and then they have to reconfigure and adjust so that they form the CO2 molecule. Right. Now the probability of this happening is way less. Right, is way less than a single bond breaking, provided you have sufficient energy. Right? So this happens. This is more likely to happen than a simultaneous breakage of 1, 2, 3, 4, 5 bonds, and then this is rearranging to produce two more bonds. So it does not happen in a single step. So it has to go through this simpler steps where this one breaks to form a methyl radical, right? And then you will have your so methane can directly react with oxygen as well, but it will produce a CH3 plus HO2 rather than CO2 and water. Right, so it goes through these series of simple steps, and we call these reactions as elementary reactions. Right, series of simple steps to basically finally give you the net product is going to be carbon dioxide and water vapor and other intermediate species, but it goes through this series of simple steps. And these are called as elementary reactions. In elementary reactions, what you will see is it basically involves breaking or forming of maximum of one or two bonds. Okay, so in this case, you are breaking one bond. Right. In this case, you are breaking one bond, forming one bond. So these kind of the number of breaking and forming of bonds is basically limited to one or two. These kind of reactions. Okay, but the net effect of all these reactions taking place in a conversion scenario is going to give you this what is called as your global reaction. So this is a global reaction, and these all are your elementary reactions. Okay, so whenever you are now trying to understand these heat release and how the mole fractions are, how the fuel and oxidizer are getting consumed. In many cases, we want to go through this, build this kind of detailed chemical kinetic model so we can simulate the various aspects more accurately. All right. So now that we have understood that these kind of elementary reactions are what are important to basically model a combustion process, we now want to understand how we can get the rate of reaction. That is ultimately what we want to do. So if you have a reaction that is A moles of A, B moles of B is giving C moles of C and D moles of D, then how can we get write an expression for how fast the A is getting consumed or produced, right? So we have a law of mass action, which basically says that the reaction rate of a chemical species, chemical process, is proportional to the product of concentration of reacting species raised to the power of stoichiometric coefficient. So when you have an elementary reaction, then basically what you can say is the reaction rate of this forward process, that is RRF, is basically proportional to your concentration of the reacting species, that is A and B, right, raised to the power of their stoichiometric coefficients, that is small a and small b. Okay, so this is proportional. So this is law of mass action, and so if you multiply a proportionality constant kf, then basically this is basically called as the rate constant. Rate constant for the forward reaction, and this does not depend on the concentration. Okay, it depends on other aspects, but not on the concentration. All right. So now, if you want to write the expression for the change of concentration of A, then basically it is proportional to the rate of change of concentration of A is equal to the change in number of moles in the reaction process minus A times the rate constant in the forward direction times your concentration of the participating reactant species raised to the power of the stoichiometric coefficients, right? So this is your expression for dA by dt. Similarly, for species B, you have the expression as minus b times kf times a to the power a, b to the power b. And similarly, you can write the species the consumption or production rates for C and D. Okay. All right. So in this case, we have assumed that this process is happening in one direction. All right. But in practical scenarios, you typically have dynamic processes in which the forward and backward reactions can happen simultaneously. All right. So because like all your reactions are happening because of some kind of a molecular collision happening or radical collision happening between the species that are present. So once you start producing C and D, the radicals C and D, radicals C and D can also interact with each other and lead to back production of A and B, right? So the reactions can happen either in the forward direction or in the backward direction, correct? So the reaction rate of AB is expressed as Kf times the participating species, and reaction rate of CD, so that means the reverse reaction is happening, that will be another constant, rate constant, that is corresponds to the reverse process, that times your C and D. Okay, so now if you have this happening, so what will be the expression for dA by dt? So in this case, if you have a reaction that can happen in the forward as well as the reverse direction, so what is going to be the expression for dA by dt? Yeah, minus A, Kf, and B to the power B. That's it. You can have your concentration of A can increase if the reverse reaction is happening. So you have an additional term AB times you have the, so for the reverse reaction, your participating reactants are C and D. So you'll have this, right? Okay. So the overall, the net reaction rate or the net rate of production of A or consumption of A is given by the summation of the consuming part that is coming from the forward direction and the producing part that is coming from the reverse direction. Okay. Similarly, you can write expressions for B, C, and D. So typically, when you look at elementary reactions in the combustion kinetic models, they are expressed in this form, and your simulation software basically takes into the overall effect of the both the forward and backward directions. So if you write a generalized in the generalized form of a reaction, so nu I is the coefficient for each of the species mi, and nu j mj are basically the coefficients on the product side. So the reaction rate in the forward direction is nothing but the rate constant for the forward direction times the product of all the participating species on the reactant side. Similarly, you can have the expression for the reverse direction as well. Okay. So now that we know what is the expression for this reaction rates, we want to understand how we can get the values of the rate constants. Okay. So the concentrations are something that you can get by measuring the species. But in order to estimate what is the determine what is the reaction rate, you need to calculate also what is the value of Kb. Okay, what is the Kb or K, which is called as the rate constant. So typically the rate constant is expressed in terms of this Arrhenius exponential form. So you have A, which is called as the E exponential factor, T to the power B. You have a temperature dependency with a temperature coefficient B, and then you have something called as your activation energy that is required for a particular reaction. All right. So what we see here is, so the rate constant is dependent on some temperature, right? And then it is also dependent on the activation energy divided by RT. So what is the activation energy for a reaction? Yeah, so minimum energy that you have to, it's like an energy barrier. So when your molecules or radicals are interacting with each other at a molecular scale, right? So you have, let's say, two molecules that want to interact with each other. So the all the interactions are happening via, so the assumption is through elastic collision, right? So the energy of these molecules have to be sufficient enough so that they collide with each other, break or form the bonds, right? So there is an what do you say, minimum energy that is required to have these molecules moving at a certain speed. Okay, so the activation energy is basically representing that component of a reaction rate. Okay, so if you look at the exponential factor E minus exponential of minus E by RT versus temperature, you see that with high activation energy processes, the rate constants are going to be very small. This exponential component is very small. So even if you go from 300 Kelvin to very high temperatures, 2000, 3000 Kelvin, you see that this component is very small. So for processes that has a very low activation energy, like for this, you see that even at small temperatures, the exponential factor is very high. So that means that these reactions that have a low activation energy can get triggered very fast. Okay, so that will determine. So when you have a detailed chemical kinetic process, okay, when you have this kind of processes, so depending on the activation energy of these reactions along with the concentration of the species, that is going to determine which reactions are going to dominate for a given condition. Okay, so there are several research groups that basically work on determining these rate constants. Okay, because they are critical to estimate the reaction rates, which again feeds into the CFD simulations. Okay, so if you look at a typical detailed kinetic mechanism file, so you can see this. These are the elementary reactions. So there is an oxygen atom reacting with hydrogen molecule, giving H plus OH, and for this particular reaction, you have A, B, and EA that is given to you. Okay, so a series of reactions are basically listed in a chemical kinetics mechanism file with the corresponding values. Okay, And some of the leading groups who develop this kind of detailed kinetic mechanisms are in Argonne, MIT, Lawrence Livermore. Then you have University of Galway, Kinetic Modeling Group by Polytechnic, Milano, and Taos. Okay, so these kind of mechanisms. So if you're using a particular kind of fuel, yes. No, activation energy is a property that of the reaction process itself. Okay, so the component of minus EA by RT is temperature dependent. Activation energy itself is not. Activation energy is like the energy barrier that is required to carry out that process. Okay, so that is constant. Depending on the temperature that you provide, this component will vary. Okay, so for this is the activation energy. Okay, and depending on the temperature field, it will calculate the rate function. Okay, so if you want to use a particular fuel, so there are online databases that are available. So if you want to use a certain species, so let's say I'll just show you a few sources which you can use. So this is one of the modeling groups, and these are freely available. So if you want to use a certain type of fuel, you want to study a certain type of combustible matter, you can go to these research groups websites, and there are kinetic mechanisms that are available, right? So if you scroll down, okay, so you see these for different fuels, right? Hydrogen, ammonia, methane, natural gas, methanol. So they have these different detailed kinetic mechanisms that have been developed. Okay, so this is one group. Then further, you also have University of Galway mechanisms. Okay, so these are your different mechanism workshops that can have developed over the years. Okay, and for these are for different fuels. So they have for hydrogen syngas. Okay, the syngas is nothing but hydrogen CO combination. Then they have built for the various types of alcohols, methanol, ethanol. Right. So now if you open one of these mechanisms, so let's downloading. Okay, so if you let's open one of these mechanisms. So these are the different mechanisms that are there already downloaded. This one. Okay, so this is a chemical kinetic mechanism file. All right. So what it details is, so if you scroll through, so it first shows what are the different elements that are involved. Okay, participating elements, and then what are the species involving these elements? What are they made of? All right. What are the species that they have? So you can see a huge number of species. All right, and after you define the species, and it's yes, it's an extensive mechanism. Then you get into the reaction classes. Okay, reaction rates. Okay, so what you can see now here is what each of these is like elementary reaction, and with each of these elementary reactions you have these three parameters that are given to you, like we saw, right? The P exponential factor A, then the temperature coefficient, that E, activation energy. So each of these is defined in this the detailed chemical kinetic mechanism files. Okay, So along with that, you also have two other complementary files that you will need for simulating your combustion processes. One is a therm file that we using which, like for each species, using this, these are basically polynomial functions of temperature. So using these coefficients, it basically calculates things like your specific thermal conductivity, diffusivity using the therm and the transport file. Okay, so along with the mechanism, okay, chemical kinetic mechanism file, you also need to use this therm and thermophile and the transport file. Okay, so all right, so these are some of the online freely available databases. So for if you want to simulate or study some particular kind of field, you can access this kind of databases and get the corresponding kinetic mechanisms. Any questions? Yes. Reaction file? Sure. This one's? Yeah, sure. Huh. No, the elementary reactions are going to be the same. I'll just come to that. So how we build this mechanisms. So this is the so for example, this is a reaction between H2.CO, right? So this reaction will happen when you have sufficient amount of these two species. All right. And the source of these two species is not, we are not interested in. It could be so fuel A, fuel B, fuel C, or situation A, situation B, situation C. If you enough number of concentration of these species, along with the temperature is sufficient enough so that it can jump that activation energy, then this reaction will happen. So typically, when we try to build, previously when they were trying to build these mechanisms, they were looking at very specific fuels, right? So when they build these mechanisms that are constrained to specific fuels, then the reaction rate parameters that they employ, they used to tune it so that it matches. The model is tuned so to match the experimental results, and now those models can be used for other species. But again, the validity of those models are specific to those particular type of fields. Okay, so to build a more universal, comprehensive mechanism like one of these ones, you need a lot more number of experimental tests with different types of fuels, different conditions, and different types of experiments as well. Okay, so right, so on that, uh, right, on that thing. So initially, like what I just mentioned, so previously when the mechanisms were being developed, they were developed based on just a single fuel, constrained to a single fuel. But recently, what has been happening is they have been making attempts to build comprehensive kinetic mechanisms. Right? What do you mean by comprehensive? So it can address these various types of fuels using the same mechanism. So the reaction rate parameters that are there, they are constant. You are not going to change if the fuel is changing. So what we do is we basically start with the simplest species, hydrogen oxygen species, right, reaction system that has 12 species and 33 reactions. And slowly on top of that, we build the C1, C2, C3, C4, and so on. Okay. So we gradually build this detailed chemical kinetic mechanisms for all the species that are of interest from a simpler molecular scale. Okay. So in this case, what happens is, if you want to simulate a hydrogen fuel system, then you don't have to change the mechanism. You can use this. For example, if you want to use a dual fuel system, hydrogen gas, hydrogen methane, then still you can use this comprehensive mechanism that has your reactions, elementary reactions for methane as well as for your hydrogen. So they are internally consistent with each other. The activation energy for each of the elementary reactions are going to be the same. Okay, so let's say you are looking at a reaction that is uh, that gives you Okay, so this is one of the elementary reactions. Okay, now this can form in a hydrogen oxygen system, or it can form in some other system. So now this does not react directly, so it has a series of breakdown. So the C7, this fuel will basically break down into a number of simpler species, and that might produce an hydrogen in between. Now, when that hydrogen reacts with oxygen atom, it still will follow the same elemental reaction parameters. It is not going to change between the two species. Will also be same. What will change is your concentration. So your H2 and O, they might be changing depending on the situation that you are simulating. But your A T to the power B exponential of minus EA by RT, these are basically coming from the reaction mechanisms. Okay, and the concentrations are being simulated conservation equation. That will change. All right. So what has been the recent efforts are building this comprehensive mechanism so that you can employ them to study various multi-component fuels and things like that. So on top of this combustion mechanism, you have additional submodels like alcohols, NOx, aromatics, so that you can study emissions. In fact, emissions predictions as well. Okay. So we can see that. So these simulations were done on ignition delay for different types of fuels, and all these fuels were basically run by a a single comprehensive mechanism. And you can see that they are able to predict the ignition delay times for these various kinds of fuels, right? So what happens is now we have various reaction classes that are taking part in these in this ignition delay simulations, depending on the temperature at which you are subjecting these fuel air mixtures to. Okay, so now these are the different reaction classes. You have a low temperature chain branching reaction, you have an intermediate chain propagation reaction class, and you have a high temperature reaction class. All right, so all these reaction classes are involved in are included in your detailed chemical kinetic mechanism file. Okay, so you can see like based on the type of reaction, you can basically estimate like calculate what are the different estimate what are the different values for A, the temperature coefficient and the activation energy. So yeah, these are the different reaction classes, and for each fuel you can have these as a submodules. So typically, like if you run reaction pathway analysis for a methane combustion system, you see that your methane basically breaks down to produce CH3, right? Then this CH3 basically oxidizes to form CH3O, CH3O2, and then it basically goes to ultimately form CH2O, then HCO plus H2O2, then CO, and then finally to CO2. So in reality, your the process of conversion of a fuel or any combustion products of combustion is going through a multiple steps through a complex process. Now the accuracy of this process is basically determined by the accuracy of the elemental reactions that you are putting in this detailed dimension. Okay. Yes.
Is there any open software is there so that we can implement this tool?
Okay, so you can. So there are some software which you can use to generate chemical kinetic mechanisms. Alright, so there is a reaction mechanism generator that was developed by Professor Bill from MIT, and that is freely available. But apart from that, if you want to use a fuel or you have a certain fuel that you want to study, you might do a literature survey. There are groups who have already developed these kind of mechanisms and they are well validated, so you can use them. All right. So the way these mechanisms are being developed is basically if a reaction parameters are not well validated or they are not accurate, then your predictions of flame speed ignition delay are going to vary compared to your actual experiments. Okay, so in that case, you have to study more about the particular elemental reaction rate and update those values in the chemical kinetic mechanism. Okay, for example, I'll just show yeah, I'll just show this last point. So So this is a, again, NIST has a chemical kinetic database. Okay, so now if you want, as you mentioned, if you want to look at a particular reaction, for example, let's say you want to look at, you want to find out what is the reaction rate parameters, rate constant parameters for, let's say, CH4 plus OH giving CH3 plus H2O. Okay, so this is one of the first steps, H2O, and if you submit, then this basically will give you. So it shows that for this particular reaction, elemental reaction CH4 plus OH giving methyl plus H2O, there are already 118 records of past studies by researchers that they have done. Okay, so if you now scroll through this, you can see that what is the reference, who has done those studies for that reaction, and the corresponding reaction rate constant parameters are also given to you. So depending on, like, you can look at the more recent studies, like you have results from 2020 to 2012. So you can look at the recent ones and you can implement, adapt them into your mechanism so that you build it more accurate. Okay. So these kind of data are openly available. So if you want to have a, if you have a commercial kinetic model that is not working well for your situation, then you can explore the any, if there are any updates to these kind of reaction rate parameters, and you can adopt it and test it. So this is one, and the other one is reaction mechanism generator. So again, this is also available. So here also, right? So here also you can do a kinetic search, and you can basically give what kind of reaction you want to look at. So C basically it comes, so yeah, so C basically reflects methane, OH is the OH radical, all right? And that gives, so we are looking at a particular reaction, and these are the various, so this also gives you a kinetic search, so where you can, which you can use to basically update your reaction. So now these are the reactions studied by various groups and published in recent literature, and based on that you can basically get what are the values of A, temperature coefficient, and activation energy values. Okay, so if you are having a chemical kinetic mechanism and it's not working, then you can, and if you want, if you're unsure about any particular reaction, then you can use these databases to update your models and then test and validate. Okay. So again, mechanism validation also needs to be done very extensively so that you know that you're not over-tuning your model to a particular condition. So for example, if you look at this validation process, so for example, let's say we are developing a comprehensive mechanism that you want to handle hydrogen CO mixtures and methane mixtures. So once you develop the mechanism, it has to be validated for all of these fuels, right? And there are different parameters that you can validate: ignition delay, speciations, speciations and flame speed. Okay, so these are the different validations that you have to do extensively so that the mechanism that you are developing is very, very accurate. Okay, and many of the groups are already working. So as engineers, you can basically take these mechanisms and use it in your simulation. All right. So with that, we will stop this session. And any questions regarding this? You mentioned about H2O2 C1 to C7 species and reaction. What about alcohol and oxidation? Yes. So when you develop this mechanism, so you are developing a hydrogen model. On top of that, you have a CO model. On top of that, you have methane and so on. So for, let's say you want to also include methanol or ethanol. So you develop the reaction module for methanol, ethanol specific to those fuels, and then you add it on top of this H2, H2CO, and H2C1 models. Right? When you integrate that, so you can form an extensive mechanism that can simulate alcohol fuels as well. There has to be. So for that, you will have specific species to that. So it is like a plug and play system. So in the base, you have your hydrogen oxygen reaction system. Okay. So on top of that, let's say you have the H2CO system, that is the next complex thing. On top, so on this now you are building, let's say, methane, right? This is where we have got. So now this methane will be having reaction specific to methane, like CH4 plus OH, right? CH3 plus O and stuff like that. Okay, which reactions you will not see in hydrogen oxygen or hydrogen CO systems. Correct. So once these reactions are taking place, it will produce some intermediate species that has H, OH, and those elemental reactions are already there in this. Correct. Now, if you want to add a let's say methanol model, right? So now you have reactions that are like specific to methanol molecule. So like methanol plus OH gives you CH2OH plus H2O. Right. So this will have some kind of reaction rate constants, reaction rate parameters. And then similarly, this CH2OH will further reduce to H2, HCHO, aldehydes, and other species. Right. So those specific reactions will be there in the methanol reaction submodule. Okay. But what needs to be done is you don't have to redevelop these reactions. You can build this and include into your kinetic mechanism file. Okay. For example, if you do not have methanol in your system, if you don't want to simulate, then you can basically take this reaction class out so that you don't have to solve for the species conservation equations for these systems. All right. So, sorry, they are not. So they are not in the fuel system. Is when you are defining the fuel composition, methanol's mole fraction is going to be zero. Right? So they are not there in your system, so it will not even consider calculating the reaction. Okay. Okay. Thank you.
Okay. Ramit, so we'll be having a break right now, and then we'll have